Значит, да, то есть, ну, по горячим следам, вот эта формула сейчас будет использована для того, чтобы разобраться.
Нет, мне наоборот трудно.
Sorry. That's right, yeah. So it was jumping between languages, right? So yeah, so this formula which we just discussed over there will be now used to the case which actually is simple and easy case, tractable case, case over 3, and it's probably known to majority of you, but I'm pretty sure that it's known in very different ways, so I'll hopefully try to connect. Right, so it will be, I call this lecture from trees to loopy graphical models. So we'll get to some loopy cases and we'll start discussing, linear programming formulation, and we'll see how many of you know what dynamic programming is? Okay. Linear programming. Okay, so there are some who don't know what linear programming. Well, then for you it may be difficult, even though I guess possible, but difficult. But I'll try to explain it. If it is first time, it may be a bit challenging, but we'll see. Okay, so that's my graphical model, but now it's a tree, and that's an exemplary tree. And what I'll be discussing has many names, and dynamic programming is one of them. Belief propagation, which is actually kind of second title of my course, if you wish. Belief propagation and beyond is another name which is associated with this case. So now what do? We compute partition function with some this normalization factor, and I basically keep here the same notations as I introduced before, and also the same notations which you saw over there. And okay, so in the case of a tree, what can I do? I can start doing computations in steps. We call it greedy, in a greedy way. Advancing from trees to somewhere central part in this, advancing from leaves towards center of a tree. Well, in this particular case, center will be, I guess, node 6. But let's start doing it kind of slow and not jumping too much to that. So what I put here is I introduce a kind of set of regions, and they're marked in a dashed way. So in this case, a simple region surrounding this node 1 is I label it 5,1 because this circle crosses this edge 1,5, and I introduce it's kind of not really good English, but partial partition functioning. So I introduce not a full partition function. You remember, full partition function is the sum of states. So now I think about the simplest possible graphical model I can imagine. In this case, it's just one node and edge emanating from this node. And there is a factor associated with this node 1, and it's factor 1. And because there is only one edge emanating from this node, so it's basically a vector of length 1, so just one component, and that's what I write in here. And I introduce, you can think of it as just the simplest possible object, graphical model, with just one node and edge. And I introduce partition function for this object, right? Z51, that's a label. And I do the same for node 2, node 3, node 4, right? And I color them in a different ways. So again, I introduce, I'll be greedily advancing from those super simple graphs, in this case nodes and edges, and of course when I have a tree I always have leaves, and I can do that, right? So that will be my first step, which is in those two lines, right? Quite simple. So then I'll be going through hierarchy, and this hierarchy consists in advancing from leaves towards center of the tree. And I choose to get next level of hierarchy. Well, this is not very large tree, so will be not very many hierarchies. So I introduce this green. So I guess it's light green, yeah, as opposed to I have two different greens. Okay, light green, right? Light green, it's a little bit more complicated graphical model. It's a graphical model consisting of three vertices and one edge. But because it is a tree, I still have only, when I define the graphical model, I have only one edge connecting this smaller graphical model, which is within this light green square to the rest. And therefore, I can still label it by edge, and in this case, it's edge 5, 6. Okay, what does it represent? It's my product of factors over all those vertices 2, 5, and 1, and then I sum over all variables which are inside this surrounding, right? So it's a variable which is 1, 5. And 5, 2, and but this partition function, I mean this graph, this variable 5, 6 is external to it, and I fix it. So it may be plus or minus 1. So sigma 5, 6. Well, I keep it in a bracket in here, right? And that's what I have for the rest. But the point is that even though I start from my standard expression, sum over all sigmas, sigma 5, and the exception of sigma 5, 6. I had here product of f's, but of course in this case I can rewrite them in terms of those z's, right? So in this case, point is that I express this partition function of a second of a graph on a second hierarchy, a second level hierarchy, through partition function of a smaller graphs on the first level of hierarchy. And then my full partition function, I will be able to write it down as a summation over only one variable. I'm sorry, I can write it down in this format, right? Expressing it through all other previous objects. So it's 6, 3, this object, right? 6, 4. And 6, 5. And 6, 5 already includes the rest. So that will be my expression for full partition function. Okay? Now, quite generally for the tree, I can write it down in this format. So I can, when I introduce this hierarchy, I go from leaves to the center. I can relate this partition function for models of a higher hierarchy to partition functions at a lower hierarchy. Well, even moreover, if my variables are binary, right? Sigma b is plus minus 1. That's, I mean, a little bit, a little simplification. I can do this type of things for any alphabet. In a binary case, this z as a function of sigma b, I can generically represent it in this format, right? With basically only two constants to be defined, a and eta. And if I'll substitute it in this formula, what I'll get a set of equations which are actually called belief propagation equations. So now belief propagation, when we, well, I'll tell you, I'll mention why people call it belief propagation. We'll actually go through that a bit later, but point is that you can think about computation of partition function in this particular case as this greedy process which goes from leaves to the center. That's how I was explaining it. But you can also think of it as a defining a set of equations, right? And set of equations which are, of course, will depend on the direction of where you go, I mean, from leaves to the center, but you can also make it much more universal. You can go in any direction, and it will be a little bit overdefined, but of course consistent system of equations. So you can write a set of equations, and what is important to understand about this set of equations. So those are equations, in this case, A I already excluded. Those are equations on those coefficients etas, which are often in this belief propagation literature called messages. And they call messages, I can tell you up front why, because this type of equations you can solve iteratively. So those are nonlinear equations, and but you have, in this case, as many equations as number of vertices, and equations for vertices, for each vertex equation, this type of equation involve messages associated with edges emanating from this vertex. So those are local type of equations. So I may have this graph, well, it should be 3 for this to be exact, but this 3 may be huge. However, I can I can answer this question of computing partition function solving these local equations on one hand, and solution of those equations usually done in iterative way, and when you do iterations in a graph manner, you can think of it as updating those etas variables, and that's interpreted as sending messages, right? So that's why those variables often called messages. Right, so it's a kind of packed slide, but hopefully illustrative and hopefully clear. So on one hand, you can think of computations which I explained here. That's how I started, as an iterative process. And on a tree, it will be just one swap from leaves to a center. Of course, will be some. I mean, you can choose how you break your whole tree in sub-trees and how you'll be advancing, but otherwise it will be a rather straightforward process. On the other hand, you can think of it in terms of solving equations. First method is, of course, what we usually do when we solve this type of problem on trees, and it's called dynamic programming. And remarkable property of this algorithm, if you wish, or approach, is that if you think about complexity of this computation, you immediately will see that complexity will be certainly not exponential, and in fact it will be linear. Because number of operations will certainly be less than number of edges, and each operation is easy, and each time you'll be adding summation over only one variable, right? So when I'm advancing from one level, for example, here, I'm only right. So well, it's actually maybe useful to. Well, I'm sorry, not over one variable. It will depend on the degree of my graph, but if degree of my nodes, if degree is, let's say, order 1, in this case degree 3, so I don't count it in terms of scaling, then it will be linear. Let's actually see it in this example. When I go from first level of hierarchy to second, so the only computation, non-trivial computation, which I need to do is to do summation here. And what the summation will be. So I'll be summing over components of the sigma 5 all but sigma 5, 6. And in this case, will be just two variables, right? So this sum, complex number of terms in this sum will be 4, right? 2 in the power 2. Because I'll be summing over sigma 2, 5 and sigma 1, 5. Each of them have two values, so overall there are four possibilities, right? And that will be the case in this dynamic programming evaluation at every step. So if my degree is, again, not a 1, let's say 3, it will be just 4 operations which I need to do. And if I don't count this 4 against, scaling and complexity, so overall scaling will be n, because I'll be each time I'll be advancing, adding 1h. We'll be going through 1h and I'll never return back. This system of equations is a little bit tricky, but you also can understand that you can solve those equations more or less in the same way, just through in one swap. Okay.
So that's for graphs with relatively small degree, right?
Yeah, that's right. So complexity immediately will blow if I have a high degree, not all degree, but that's nothing you can do. Complexity also will grow if you have a high alphabet, but if high alphabet means that not plus minus 1, but let's say 1, 0, 0, 1, 2, or so size of alphabet will be exponential dependence on size and will be exponential dependence on degree. But if size of alphabet and degree are order 1, then overall it's very good scaling, and it's linear in the size of the system, number of edges. Okay, so now this dynamic programming and belief propagation actually pop up in the various places, and it's actually very long history. Probably the first papers in physics, in fact, which mention something of that type, not focusing on complexity at all, and not discussing, in fact, trees originally, but reducing problem, simplifying it and reducing to trees. It was these famous papers by Hans Bethe and Rudolf Peierls, famous physicists. Well, then, of course, much later, also people in spin glass community did quite a lot of that. We also know it as a dynamic programming. We usually refer to Bellman. And Bellman, it's used very heavily in control and optimization. In information theory, in this coding theory, these graphs, which I showed you but didn't explain in details, so-called low-density parity check graphs, ideas behind decoding of these graphs very much related to this dynamic programming, and is by Robert Gallagher. Well, this famous, maybe you've heard about it, famous Viterbi algorithm. Viterbi is founder of Qualcomm. He is one of those few scientists who managed to turn it into billions, probably. So Robert Mackay, I mentioned his book. He also contributed to that. Name belief propagation was tapped by Pearl, and that came from artificial intelligence. Just by incident, belief propagation, BP and beta piles is also BP, so we kind of use it as a BP. But it's certainly related to dynamic programming. So now where difference start? Difference will start when you go from trees to graphs with loops, and that's where what we'll start discussing next. And let me back up. Remarkable thing about this view on a tree computation is that I got equations, right? And when I wrote these equations, of course, to derive them, I use tree logic. It's correct only if I have a tree. However, when you look at those equations, you realize that those equations are local, and I already tried to stress it. Let me stress it again. Local in the sense that I have as many of those equations. There is this index A as number of vertices. those equations involve messages, variables, which are just real numbers from minus infinity to infinity, which reside at edges, and actually two of them, it's kind of huge. Well, eta AB and eta BS, they're not the same. So those variables, they're associated with edges of a graph, right? But edges which are linked to this node A. And I have many nodes in my tree, and for each node, only variables which reside on the neighboring edges enter these equations. And I have many of those equations. So there is a very nice and serious factorization. And when you look at those equations, and you're not picky about how those equations are derived, you realize, oh boy, I have it. Well, there is nothing about a tree in this equation, right? So if, well, I can think about arbitrary graph, and I can think about the set of equations defined in arbitrary graph, try to solve them. That was logic, which was very non-mathematical logic, very kind of, well, ad hoc, and people who apply it realize that. However, their thinking was along the lines of, well, if effect of those big loops, what distinguishes trees from graphs with loops, loops, right? And if loops are very large, that's probably not a bad approximation. And in fact, when you have this sparse graph, and for example, this low density parity check codes, there are graphs behind, and they are sparse. Sparsity means that loops will be very large. So that was, Robert Gallagher suggested it, and the assumptions behind it, so it was not mathematical suggestion, assumption behind was that effect of those long loops may be not important. And a lot of stories are about belief propagation stories, about applying this as a heuristic. Heuristic means that, I mean, it's not guaranteed to be exact, correct, applying it to graph with loops, and then analyze, and then try to see either theoretically or maybe empirically how it works. So that was the beginning of this belief propagation story, Peter Pyle's story, and derived for trees, but then extended to cases when there are loops. And we'll.
How is it?
Huh?
How is it works? I mean,
well, that's what
quite well, or not?
That's in many cases works remarkably well, and there are even theoretical foundation behind that, and that's to a degree what this course is about, figuring out and analyzing why this is successful. There are always counterexamples, so there are cases where it doesn't work, but even those cases are quite instructive. Yeah, so it's. Short answer is it works pretty well, and even in a case, well, it's not super surprising to expect that it works well in the sparse cases, and when, how we call it in physics and computer science, there is a decay of correlations. So somehow, when you go along the loops, you forget about what was in the beginning of the loop. So in this case, again, intuitively, that's probably good.
So if the loop is long, then it's okay.
Well, that was the original thinking. But remarkably, it works also very well in many other cases when loops are actually not very long and graph is rather dense, and we'll be discussing those cases.
Sorry, one question about the example. In the example, you calculate the statistical sum, but what is the optimization problem? You say
well, that's what I mentioned. I said that there is maximum likelihood problem, right? And there is a partition function computation problem. So we'll be discussing both of them. There is a way to relate them through this temperature in physics, but partition function computation is more difficult problem in general, and that's what we are focusing on in the first place. But actually, even in this lecture later on, we'll get to to maximum likelihood.
My question is, what is the connection between dynamic programming and the previous example? Because you just
okay, good question. I can actually formulate in a very similar way dynamic programming for optimization, for finding maximum likelihood. So now instead of sum, will be max. So basically, I'll be. It's exactly that. So it will be also greedy. So I'll also be advancing from leaves to the center, but instead of summing over all those variables, for example, in this green box, you remember, right? So I was in here in this line. I was summing with respect to variable 5.2 and 5.1. Now I'll be maximizing. So I'll go through this four states, right? Because there are two variables that are binding.
On each step you solve the optimization problem.
Right. Yeah. So actually, in many cases, yeah. So and this formula will also be. I think yeah. So summation will be replaced by max. Well, there are various ways to understand how it works. The simplest way to think about optimization as a maximum likelihood computation is following from partition function. Replace those f's, but exponent minus, and then there is energy depending on the sigma a. But send energy to infinity. So basically consider limit. That's what physicists call zero temperature limit. And effectively, it means that these f's will be very peaked, right? And it means that this sum will be replaced by maximum. So, and that's as simple as that. But optimization problems are often much easier. In this case, they're all easy in the same way. I mean, in the case of a tree. Right, but now I'm getting to what is heuristic story, and heuristic story which will actually start from this formulation which we have here on the board, and it's again reproduced in here. That's what we discussed half an hour ago, and that was instead of computing partition function, I was telling you how to rephrase this problem as an optimization problem, right? So now I want to take advantage of this formulation and get, actually quite surprisingly, to something which is similar to what I just showed you and called dynamic programming and belief propagation. And okay, so how will I be doing that? I'll be, as I explained, it's just kind of formal reformulation. It's nice because instead of, I related counting to optimization, but it's absolutely not tractable. Too many states. So what do we do in this situation? Well, we are trying to restrict. We are trying to come up with some good factorization and probably restrictions on this b's over which we will be optimizing, minimizing, right? So I arrive at optimization problem and I have too many variables and I want somehow to reduce number of degrees of freedom. And one way of doing that is so-called mean field. Okay, so what is mean field in a probabilistic, stated probabilistically? Mean field is a term which physicists coined this way, and I think it's now used also quite universally in all those disciplines. So here my variational variable is probability, right? B of sigma. So it's my, we call it belief, and it's proxy for probability, right? What I can start making assumptions about this B. And one, maybe simplest assumption is that assume that all those variables, my original variables are on edges, right? The sigma AB I associate with each edge. Let me assume that all those variables are independent. what does independence mean mathematically? It means that this B's is factorized and I can represent it as a product, right? So product of probabilities of individual variables altogether result in a statistical independence, right? And of course, it's by no means clear if it has a sense, and in fact, it's certainly not correct. In fact, even in the tree case, we know that it's not correct, but in general, for mean field, there is no case when it is correct exactly. But I didn't want to discuss a lot this mean field, in part because it's actually much less successful than belief propagation, but a story behind mean field is whenever you have variables which you have reasons to assume that they're statistically independent, that's where you use mean field. Okay, so, but now we are in the following remarkable world of variational ansatz, or variational approximations. And again, anything here, what I'll be explaining in the next 2 or 3 slides will be approximate. We'll get back and try to make it rigorous or almost rigorous later. For now, it's just, I mean, intuitive and nice, but approximate. So what is good about factorizations, for example, of this type? Instead of having 2 in the power n variables, right? So how many variables do I have in here? I have this BAB, probability of belief associated with proxy for probability associated with H. And it's already marginal probability, right? Or marginal belief. This BAB, sigma AB is plus minus 1 or 0, 1. So there are only 2 variables per H. And actually, because BAB is probability, right? BAB of 0, let me call it in terms of, talk in terms of 0 and 1. B of B of 0 plus BAB of 1 is still equal to 1, right? So I have this normalization. So there is in fact only 1 variable per H. And I have, well, as many variables as number of edges. I reduce myself from 2 power n to n. That's very good. If it is correct, if it would be correct, that's remarkable, right? Now, interesting statement is that there is a very similar factorization which you can do on the trees, which will be exact on the trees, which will not be exact in general. And that's what allows me to reinterpret what I told you before about this dynamic probability belief propagation in a variational way. And this is ansatz which you need to put in, and this ansatz is for a joint probability distribution expressed in terms of marginal probabilities. And I hope these notations are clear, right? So, okay, maybe I'll go there and try to clarify it. So, well, B is, when I use B and not P, you always call it belief, and that's, I think of it as a proxy for P, and proxy in this variational sense, right? So I'll be substituting B's in my functional, and then we'll be doing variations. So now I also introduce this BA sigma A, which is what? Which is marginal probability. So I take this B of sigma and I fix. Oh, it's reflecting, I see. Then you cannot see it, right?
Включить обратно.
Yeah, I see.
Maybe you can use black. You can use black pen.
Maybe. Is it reflection? Or what is the problem? Or you don't see?
That's okay.
Actually, because from my angle I see it really well. I'm not sure.
Oh yeah, we can take another one from the outside.
Okay, maybe.
Green,
Yeah.
green. Okay.
But right, so this is marginal probability associated with vertex. This is marginal probability associated with edge, and I define it in exactly the same way. So now, okay, so you remember these notations, right? I sum of all variables by sigma A. In this case, all variables by sigma AB. Right? So I have these marginal probabilities for associated with vertex. I have marginal probabilities associated with edge. And a remarkable statement which you see in there in the second line, and I stated that it is exact on the tree, that there is this formula. So maybe I'll now get back. Sorry for jumping back and forth. Yeah. So this formula, I'm claiming that this is exact on the tree. I actually leave it as an exercise for you to see why it is the case, and maybe a hint to prove this formula. You actually do very much the same as we did when we discussed dynamic programming computations. Basically you first prove it you do it by induction. You first prove it or show it for a very small graph, and then you start extending it. Okay, you first show it for the simplest possible. So, well, I guess one node, then you go from one node to node and number of nodes connected, and of course you do it for the tree, and you show that this is the case for the tree. It's quite non-trivial. So now intuition behind this formula is actually a little bit. So this proof, well, for some people it probably will be intuitive. For me, what is more useful is to think about this formula in the following way. So I first actually prefer to think about it as a kind of extension, extension of mean field, extension in the sense that I first start thinking as a kind of about it as a mean field, and then introduce correction. So correction is here in the denominator. First, forget about that, and you'll see that it's almost like mean field, right? So what I do, I have vertices. Well, mean field was written as a product of objects, marginal probabilities associated with edges. But if I close this part, it will be product over vertices, and I have these variables associated with vertices, which is vector sigma A, right? And first, let me assume that they're independent, and then I have what is written here, and it will be pretty much kind of mean field type of argument. But of course they are dependent. Why they are dependent? Because if I have two vertices, there is edge which connects those two vertices, right? Well, if those vertices are connected, there is edge connecting vertices, there is variable sitting on this edge. So this variable, I counted it twice, right? So it enters in BA, and it also enters in BB, if there is an edge between A and B. And what I have in the denominator is a correction. It enters twice, so I put BAB, well, because each edge in the graph, unless it is the end point of a tree, each edge enters twice. Yeah, so, right, and so that's basically logic. So it's a kind of correcting for correlations which I ignored when I put nominator, right? So denominator corrects for that, but it may be useful, maybe not for some of you. It's straightforward to check. So now what you see in here are constraints, right? So my marginal probabilities, of course, marginal beliefs, I want to think of them as probabilities. And for every vertex and for every edge, or every neighbor of this vertex, well, first of all, for every vertex, I have this formula which sums all those BA sigma A to 1. And then there is this relation which is also quite obvious, right? So it's a relation between, I didn't put it over there, but so what it states in here is that if I take belief associated with a vertex, and then it's already marginalized with respect to all variables but those which sits on edges next to emanating from this vertex. And then if I sum up over all variables by one associated with some edge, then of course I'm getting, so in this sense I'm fixing sigma c. Then I'm getting this marginal belief associated with edge, right? Relations between beliefs associated with edges and beliefs associated with vertices. Notice that all those relations are linear, and that's actually quite significant. So now, if I'll take this ansatz, substitute it in here, replace my b by by BA and BAB, and also account for all those constraints, I'm getting, so here I have a functional of beliefs. I restrict my space, right? Instead of discussing these beliefs most general way, I only restrict myself to beliefs written in this format. And then its approximation, obviously, I'm getting functional, which is called beta free energy. And this beta free energy depends only on BA and BAB. It's written here, and I can tell you I can give you some intuition about all those terms. So the first one is actually called, if I use terminology from physics, self-energy. And these other terms, they're called configurational entropy, and in normally entropy appears, as some of you probably know, as B log B. So here I didn't assume it, I just derived it. But that's clearly entropic terms, so it consists of sums and minuses of those B log B contributions. This minus originates from a fact that I had, in the Mill field case, I would have everything plus, because my ansatz was just product. So minuses are coming from the fact that I'm dividing here to this product of BAB over edges. And actually, this minus create quite a lot of troubles in terms of analysis of this new variational problem. But important thing is that never mind remaining complications. I'll be discussing what can we get from this stage. There are a few important things. So first of all, this is clearly not exact in general. It will be exact only in the case of a tree. B, well, I guess many of those points in here. Exact on a tree. Probably most important thing, why did I do this? I traded optimality for efficiency, for reduction in complexity. So I had 2 in the power L in this case. L is a number of edges. So I have a serious reduction from exponential to linear. And again, I'm assuming that everything is degrees of nodes in my graphs are order 1. So I'm not counting degree in the sense of scaling. Okay, so now I'm discussing here optimization, right? And in fact, in this course, mini course, I'll not be focusing too much on how I solve those optimization problems, unless in some cases I'll be able to reduce it to convex optimization, and then I'll basically say that, well, we have a nice solver. So, normally people solve them in an iterative way, right? So you introduce iterative algorithm, you solve optimization, and there is a whole thing about how to design those algorithms, convergence, etc. I put it under rack. During this course, I'm not focusing on that. Maybe somebody will, of those who wants it for grades, will select it as a project, and we will then discuss it beyond lectures. There are a lot to discuss. It just, I think it's much cleaner logic when you separate iterative algorithms from formulations. So here I focus more on the formulations, assuming that if optimization is reasonably nice, we'll find a way to solve it. And I mean, it's more like disclaimer. I understand and I appreciate the fact that this iterative part is by no means simple indeed. Okay, so now, right, this. Right, so that's another remark about iterative algorithm. Let me, not focus too much on that. Okay, so that's probably most important thing in terms of consequences. Because of this, because of number of things, I'm getting, as before, I was telling you, it's already raised, that this variational formulation of counting problem, exact formulation, allows me to compute partition functions. Here is the same. I'll be computing approximation for partition function. I'll be calling it ZBP. Z is our notation for partition functions, so ZBP is what I'll be computing by solving this optimization problem. It will not be exact. And now interesting question is, if it is not exact, is it upper bound, is it low bound, how is it related to exact? Can I make any statements? Unfortunately, in general, not. For some problems, we can make this statement, and that's what we'll discuss later on. In particular, for attractive, so-called attractive graphical models. And it's actually very, in full generality, to prove it is rather non-trivial. And it was done 3 or 4 years ago in a full generality. But on one, you may say, okay, then what's the use of it? Practically, the fact that we are not, sometimes it's upper bound, sometimes low bound, is actually, practically, empirically, it's a good news because all other approximations which are either low bound or upper bound, they're usually very inaccurate. So there is what we call big gap. It's a price you pay for being quite good in a practical terms. So at least that's my take on that. Again, empirical take. And maybe I'll leave it for another question, kind of exercise question. We already have this question of how to get this formula on a tree. And now, if you can think, and maybe we'll discuss it briefly in the beginning of next lecture, why this ansatz is not upper or low bound for belief propagation for exact. In fact, the hint is that mean field is in fact, because it's a relaxation, it's a upper bound, it's a low bound for partition function. That's another question which I hope you'll think about, and then we may discuss either in the beginning of next lecture or kind of offline. So belief propagation is not of this type, and there is a particular mathematical reason for that, and if you can try to figure out why by yourself, so that would be good. Okay, so now maybe in the last part, in fact I have more slides for this lecture. I'll probably skip some of them, and I'll be doing it in all lectures. So there will be more material in slides than what I'll be discussing. And this extra material, you're very welcome to ask questions after you'll see it, and we can also discuss it offline. It's just for maybe fitting it in this framework. We can also put some of that into this project part if somebody will pick it as a project. Okay, so now maybe close a link to what I know is of interest for some of optimization folks in here. Remarkably, well, so far I was telling you about this beta free energy, belief propagation, stated as variation, and I was saying that, well, empirically is great, on the trees is exact, but you may ask, and I was mainly focusing on partition function. Now, how how about optimization problem, maximum likelihood problem? And again, just to remind, maximum likelihood problem is finding, not counting all states, not computing partition function, but finding one configuration sigma, what I call state, which is most probable, right? And so let's first think about what is a version of this problem within this language or framework of belief propagation. And remember I was calling those different terms in what we call beta free energy, self-energy, and entropy. Maximum likelihood version of the problem basically consists in completely ignoring entropy term. And well, again, if you're from physics, it's quite natural, it's just zero temperature limit. It requires a little thinking if you're not, but it's rather straightforward. And that's what I'm doing. I completely ignore all these B log B terms, and I'm keeping only linear terms in B's. And my constraints are all linear.
Are there explanations why you can ignore B log B terms?
Well, okay, so one simple explanation, intuitive. I remember when it was this question of, well, when I was trying to explain the relation between partition function and maximum likelihood, I suggested to think in the following terms. Think about those F's, which are very peak. I have a product of factors, and imagine that those factors, each of them, they're peaked around certain configurations. So basically, they are practically zero everywhere else. Not necessarily exactly zero, but practically zero. Then, those F's, those factors, well, one way to think about picking them is make these F's very large at certain configurations, right? Therefore, those terms will be unbounded. B log B is always bounded. B's are all probabilities, they are between 0 and 1. B log B is between 0 and 1. It will be bounded by number of those terms, and this term will not be bounded. Okay, so at least that, mathematical type of explanation. You can also get it more or less directly through, well, in other way, as I was telling you before, replacing sums by maximum. But point I was trying to make is that you're getting a problem where you minimize linear function. This is linear in respect to B. Under linear constraints. And that's, of course, linear programming. And for those of you who first time heard here about linear programming, linear is the simplest possible optimization you can imagine. So you have linear objective. So you optimize over your variables, in this case B's. You have linear objective. So what optimization entails? You have objective which you minimize, and then you have constraints, and the set of linear constraints. And set of constraints, well, I didn't write them down in here, but they were written. Okay? And again, all those constraints are linear. So I have normalization constraints, I have relations between beliefs associated with vertices and beliefs associated with edges. Well, I also had inequalities, well, which I wrote somewhere that all those beliefs are probabilities, so they should be more than zero. Everything is linear, right? So linear programming is when you minimize linear objective and the set of linear constraints. And well, linear programs are very good optimization problems, as we know. So there are multiple remarkable algorithms to solve them efficiently. Actually, people from this institute contribute to this field a lot. So I'm certainly not planning to discuss details of how exactly we solve linear programming, but I mean, simple statement or simple knowledge which we'll be using that it's good to have linear programming, and we have plenty of algorithms to solve them. So now, so that's good news, right? So I at least in terms of computations, those terms, when I have my partition function computations, makes problem non-convex, which means not really nice optimization problem, difficult problem. So in the some degree difficult. In the linear programming world, everything is nice. And well, just as a matter of reference, in the context of error correction, this graphical model, so-called graphical codes or LDPC codes, that was introduced by Feldman, Van Rijt, and Karger in 2003, relatively recently. And that's how I got to know this, I mean, how I entered the subject. But remarkably, in all other disciplines where graphical models were used, this fact was also not appreciated till the last 10 years. And basically there were quite a lot of interesting stories about that. And okay, so why we got excited about this linear programming? It's actually not a general purpose linear programming, for those of you who know linear programming. It's linear programming over those beliefs and between 0 and 1s. And one useful statement is that when I started from this, when I was discussing partition function, and I was reducing myself from problem of counting, summing, to optimization, there is analog of that, which I can introduce optimization analog of that. So I can start from optimization problem when I optimize over binary variables, plus minus ones, those sigmas, and then I modify it and I reduce myself to optimization over beliefs. And beliefs are continuous variables between zeros and ones. So I can do it, and this will be exact, but very much like in the case of partition function story, this new optimization stated in terms of beliefs will be linear programming too, but number of variables will be exponential, as in my problem with partition function. So therefore, I can ask a question of how this formulation, which is already relaxed, already reduced, relates to my original formulation, original integer programming formulation, or maximum likelihood formulation, my optimization problem, right? Maximum likelihood. And remarkable thing which you can state, well, is actually written in here. So first of all, well, I guess, did I put it? No, I didn't. In fact, I do have something which is rather formal in here. Let me maybe not use it. Let me explain it in words, and then we'll finish on that. Right. So, well, everything in this slide is written as it would be for LDPC codes, but it applies for specific problem, but it applies for all those graphical models we are discussing. So this, first of all, this LP, which I put in here, which is, I call it BPLP, is in fact a relaxation. It is a low bound for exact. It is quite different from what I told you about estimation for partition function. For partition function, it may be low bound or upper bound. But for what we call LPBP, it is always low bound. And the way to show it is to go through this reformulation of your original problem, which is integer programming, which is not linear, to integer linear programming stated in terms of, I'm sorry, not linear programming stated in terms of belief, so this will be exact. And then introducing relaxation. So this, what relaxations mean? Relaxation mean that this polytope, which you start from, which was originally in terms of polytope is a set of linear constraints, right? We call it polytope. So I mean domain, which is defined in terms of general beliefs. You basically can understand this DPLP as a relaxation of it. I have a couple of slides with the formal kind of dense in terms of formulas, and I'll show you, but I first wanted to say it in words. That's actually, yeah, it's not here. Maybe practically most important thing, if you solve this linear programming, which is approximate, and if you're getting 0-1 solution, then it is certifiably exact solution of your original problem. I'm not saying that you'll always get 0-1 solution, but if you get 0-1 solution, then you solve your original problem, which was difficult. So there is a very nice certificate, which is actually.
But for which type of structure?
Well,
is it a tree or what?
No. It's a generic.
So if the solution
is
0-1, then even for generic structure we'll get
exactly.
it is exact.
Exactly.
So now you're speaking about this relaxation when you place binary by continuous from 0 to 1.
That's right.
Yes.
So again,
that's lower bound just because like you increase space, right?
Well, that's what I was arguing, but it's not. Yeah. Let me. Okay. Since we are in any case talking formally here, let me. Well, I didn't want to scare everybody, but that's where we are getting. Actually, there will be few slides which are very general in the sense that, so it probably will take not more than 5 minutes, we'll finish soon. So this, here in this next 4 slides, I'll be discussing, I'll not limit myself to binary alphabet, okay? And I'll be I change from my sigma variables, which were binary, to x, and x may be from any alphabet. And that's actually formally what is stated here. But important line is this line. So I have my original problem, which is general purpose optimization problem. I didn't specify anything in this optimization problem. I only assume factorization, right? And factorization in terms of optimization, in my partition function story, I have a product of factors, right? When I want to find most probable configuration, I basically maximize probability, and then I should think about those f's which I had there as a kind of f's which I had in my first slide. You shouldn't confuse them with those f's. So my original f should be exponent minus f which I use in here. Okay, sorry for. I'll actually change it in the PDF file tonight. So let's call it, I don't know, whatever, G. So, but this is my general purpose optimization problem, which is factorized. Okay. So now, what I can do with this problem, I can do transformation from this general purpose optimization to what I call exact linear programming. And here I introduce this, well, maybe a bit ugly, integrals, because I'm not restricting myself to any alphabet, and alphabet may be continuous. But think of those integrals as sums, okay? If you prefer to think in terms of discrete variables. So now, basically, this step is a completely equivalent to the step of transition from when I was discussing partition function, from sum over sigmas to optimization over b's. So that's very much the same. So, but here I transition from minimization of a general purpose function to minimization over beliefs, over those probabilistic variables. And well, here I minimize under constraint, and constraint I stated as these beliefs belonging to polytope. And well, that's polytope is this domain which is bounded by inequalities or equalities, and those equalities and inequalities written here, and they should be familiar to you already from my. It's a little bit different notations, but it's basically what I was telling you before. Again, modular these corrections that now I really discuss, not only binary. Okay, so this is exact. So it's a reformulation of my original optimization problem as linear programming. I'm not gaining anything. This linear programming over a huge set of variables. Actually, in continuous case, it's a continuous set of variables. It's, infinite. But the point is that I can actually massage this problem and do relaxation, what an optimization literature is called relaxation. What relaxation means? Relaxation means that, well, in this case, I actually will be doing relaxation in kind of two or 2.5 steps. First of all, I modify my exact polytope in the following way. I extend it introducing auxiliary variables. And those auxiliary variables are those beliefs associated with vertices, BA, and beliefs associated with, so I changed notations here also a little bit. So, okay, so since already late, let me schematically tell you that, and then we'll probably repeat it in the beginning of next lecture. So I extend my my description going from my original beliefs to beliefs, those original beliefs plus those marginal beliefs. And marginal beliefs I'll just define as marginalization of my full beliefs, right? So what I'm doing in this step, I'm just expanding state. I'm introducing additional variables and define those variables. So in this sense, it is an innocent step, and I can of course do it on optimization always. But then I get rid of all my original variables, B's, and basically killing those lines, and this is exactly what is called, what is a relaxation. So when you have a polytope and you get rid of certain constraints in this polytope, you are relaxing your problem. You are in your minimization, optimization, which is minimization, you're getting low bound, right? So that's, in optimization, we also call it cutting plane, right? So you basically get rid of one constraint or many constraints, and by doing that, if you're solving minimization problem, you're getting a low bound, right? You're making your problem simpler. You are probably losing something, but that's what relaxation is. And this, what I call LPBP polytope, it's already small in the sense that it's stated only in terms of those beliefs, not exponential number, but linear beliefs associated in my original notations with vertices and edges. And there is a consistency constraint between them, positivity and normalization, but it's all, nice, good polytope. And that's what I'm getting. So I'm getting this relaxed LPBP formulation. Okay? So now, it just, details are difficult to digest from slides, and those who want to understand need to try to work it out, and probably it's better to work out on a simple example. But statement is, and now maybe I'll be back to what I had in here. So statement is that this LP formulation gives you low bound. This low bound is it's a generic statement for any graph. There is a certificate which also comes automatically through this logic, and certificate again means that if in the result of optimization you're getting 0-1 solution, it's a continuous optimization, right? So it's a linear programming with all variables between 0 and 1, and if you're at the corners of polytope, if what you're getting is 0 and 1, which means that you're this polytope, which you get in here, is not necessarily integer. So there are corners which are not integer. And you can get to those non-integer corners. Linear programming always result in your optimal solution being in a corner, right? Because your objective is linear, you cannot be stuck in the middle of your polytope. You're always in a corner. And you also cannot be on the side, unless the generous and degenerous are ignored. So you're in the vertex. But vertex is an integer or not. And if they're integer, you're done. So there is certificate. And your unique case has low bound. So that's very significant and nice property. And in fact, later on, we'll see that. So you may, based on that, you may ask question when you can actually prove or show that there is no gap, that gap is reduced, that you're always getting integers solving this problem. And I'll tell you later on, well, there will be a number of problems for which you can prove it, and those problems will be with a lot of loops. Actually, those slides which I skipped, you can look at it. Well, it's one particular example, the so-called ferromagnetic random field Ising model. This Ising model which I was discussing, but also with additional linear term, which is this H is maybe plus minus, I mean positive or negative. All J's are positive. So for this particular problem, gap is 0. And again, it's only for solving the respective optimization problem, finding maximum likelihood. Okay? There are other problems of that type, and we'll be discussing it well, in more details later on. So I guess I'll finish with that, and next time, let me maybe show you the plan for next. So we'll go into, we'll get back to partition function, and we'll be discussing well, the story of loops and how to make this belief propagation, which was ad hoc approximation, the way I introduced it, actually how you can correct it to make to close the gap for partition function, to compute partition function, at least in principle exactly. I'll not solve all problems, but it will be, yeah, some framework which you call loop calculus, which and gauge transformations, which will be quite useful for reformulations and good approximations. So it will be after tomorrow, and again will be 2 lectures. Okay. Thank you.
Коллеги, большая просьба, стулья, кто где-то брал, вернуть их там, где вы их брали.